So this is generally what I do is I try to plan a vision for the next decade. Like I try to create a vision for, say, a 10-year vision, and then of course I never succeeded in achieving my vision, but it gives me a guideline as to which way to go. So I'll sort of talk to you about what my vision for the next decade is actually. So we want to create I'm actually known for the work in oxide and oxide interfaces. And this field is turning out to be incredibly exciting with a great deal of quantum functionalities that we're seeing at these interfaces, which can be controlled by, say, electric and magnetic field. And the next generation of, for example, low energy memories and devices that Intel is working on, for example, will be using many of the concepts and ideas developed in this research field. So, for example, there's a 2D electron gas naturally formed at the interface of oxides, which has got a tremendous potential to be modulated for creating all kinds of new phenomena. Superconductivity, ferroelectric interactions with the oxide interfaces, and very large spin orbit interactions leading to novel spintronic possibilities. And then there are topological states like fermions and neurons, anti-neurons, and these are actually topologically confined spin states, and they have potential in what I call novel memory devices, and it's still, we haven't figured out how to manipulate them, but these are really very exciting things that are happening in this field. So this is something that this is a field we are actually establishing. The other one I would like to do in the next 2 years is to establish AI-enabled centers, and one is on Advanced Center for Brain-like Electronics, and then an Institute for Volatile Organic Compound Studies and Applications. And I'll just give you a brief idea of what these centers would be like. See, essentially, the Center for Brain-like Electronics would be a research institute with the best of the university, and it's a very interdisciplinary program, and will involve, also globally a large number of. Already I have a team of global collaborators in this thing, and get something like a Kavli Institute to it, make it very attractive, and involve not only just device and material scientists and computer science people, but also neurobiologists, which I think is very critical. And of course, there'll be a lot of entrepreneurial things that come out of it. And when I was at Maryland, my students ended up creating about 18 companies. So, I think so. I see a lot of potential for creating entrepreneurial investing in this. Now, let me talk about volatile organic compound detection and application. Why I think this is really, which ties in with the AI and machine learning in some way. But it's very important because, for example, in my group, one of my students, we study the human breath and the molecular content of the breath. So our breath produces something like about 3,000 volatile organic compounds. We are like a biochemical factory. But fortunately, these are produced at like 100 parts per billion and below, very low level. Otherwise, we'll all be stinking like crazy, basically. So, so the point is that the thing is that this pattern of this molecular pattern is very disease specific, right? So we, for example, my student for her thesis, she looked at 7 different lung cancer cell lines, and by just looking at the VOC above the cell, you could actually predict which is the cancer cell that is. So we started working with the lung cancer.
What does VOC stand for again?
Volatile organic compound. It'll be like acetaldehyde, right? Acetone, ethanol, methanol, all of these are VOCs basically. And our body produces all of these things.
How does this compare with the effort by Intel?
Pardon?
Intel 4 years ago, inspired by medical experiments where medical dogs actually were detected by a cancer exactly by using their superior characteristics of their nose.
Right.
Intel called for a competition to create an artificial nose which will have similar characteristics. How does what you do compare with that?
Right. Okay, so I'm going to tell you in a few minutes. I don't know about the Intel competition because I wasn't that out of that one.
Right.
But I'll tell you what the issues are. So what we did is we essentially looked at a bunch of lung cancer patients, and this is it's a principal coefficient analysis plot, the statistical plot of the data, and you can sort of see we can completely separate out the lung cancer patient from normal people just from the birth pattern. But we found there's another group sort of developed here, which we thought these were all lung cancer patients, but it turned out that on further analysis, these people are tuberculosis patients, actually. So that's the power of this technique, that we can really, the beauty of this technique is that it's non-invasive, and I'm going to see in 10 years' time, this is going to become very important. And so we have actually formed a company called Breathonics, and we're setting up a mass spectrometer inside an emergency room of the second largest hospital in Singapore to start looking at, cardiac patients, basically, to see, can you tell someone who's got a myocardial infarction, then someone comes with a chest pain, can you tell that very quickly by looking at the...
Can you characterize the discriminating power of these schemes and algorithms by numbers such as X molecules or per million something?
Yeah, essentially, that's the whole idea. Essentially, what we do is, we do a normal person, we do, let's say, the molecular pattern of a normal person, and you take a lung cancer patient, you take the same thing, and you suddenly look at which are the molecules which are changed in a dramatic way. So you create what's called a heat map, basically. And that tells you, so to really do this predictive thing, we take roughly about 8 to 10 molecules based on the heat map, and we essentially patent it. We patent these molecules for that particular disease, basically. Those are the biomarkers, basically. And then, so that's how we do it. Ultimately, what you want is these to be in the form of like chips, some kind of an optical chip, and it turns out that all these molecules have resonances between 2 and 18 microns, basically, in the mid-infrared. And so to develop, molecular resonances, you like to use like integrated optic techniques. So, for example, hyperbolic metamaterials and things like photonic bandgap resonators, and there's a variety of other techniques by which you can do molecular sensors. So the molecular sensors, in my mind, is going to be a way of the future. To have an institute where you can really make molecular sensors of all kinds would be very impressive. You need to have high sensitivity and also selectivity is very critical. The reason is in the mid-IR, right, these vibration frequencies come from C versus C double bond Cs. And you can see, methanol and acetone will have very common bonds, actually. So just by looking at one frequency, you can't really get specificity. You need to look at many frequencies. So how do you design, cleverly these type of sensors? But again, this is also pattern recognition. So AI and machine learning is just perfect for this, really. So ultimately, these technologies will involve AI and machine learning.
Yes, I want to go back to artificial node, right? Since I work in Germany, I know that the Germans have a fantastic artificial nodes. I don't know how many different molecules they can detect.
Right.
The major application is, of course, to detect the quality of beer. Okay. But that's the side effect. The point is that what you said correctly, we're trying to design and using inorganic material, right, electronics and stuff like that,
right,
sensors that mimic the specificity of the dog nose. And the end is designed by 1,400 particular sensors, all tuned, as you just said, to a particular molecule. So where are we going with this technology?
No, well, what we have realized is you don't want to focus on a single molecule. Right. Because if you take a molecule like acetone, right?
No, not single molecule. I see. You get the collections of molecules.
Yeah, you're going to have a molecular pattern. In other words, you pick like about 7 to 8 different molecules, and you create what you really do is what you create a heat map. You look at all the molecules, normal person, disease, person with the disease, then you look at which are the molecules that are enhanced in the diseased person, right? And there you'll actually find that are something like 7, 8 molecules. And it's very good to have more than one molecule because very often, many different diseases, that same molecule may be enhanced, right? But a pattern of molecule is very unique to a particular disease. So that is the reason why this whole field, requires some smart way of pattern recognition. And that is why this is an AI and machine learning enabled technology is going to play a very important role. Yeah.
When you see pattern, it's not only the combination of the VOCs, but also the concentrations will relate to each of those VOCs.
Exactly. I mean, in other words, you will have some kind of what I call a normal distribution of VOCs, and how much are they deviating from that? And that will be very important for this. Yeah. Absolutely. Yeah. Right.
Yeah. So, Venky, you differentiate between the LAGs, the cancer cells, and the other ones by heat. By the heat signature, or how do you differentiate? Is my question.
You mean in this year?
Yeah. That simple thing.
No, in this case, what we've really done is basically we looked at the molecular pattern we identified roughly about 8 to 10 different molecules, and we just essentially looked at the molecular patterns, basically.
Okay.
So this actually corresponds to one set of molecular patterns, this one corresponds to another set of molecular patterns, and this one corresponds to another set of molecular patterns,
Okay.
basically. And so they just separate out in the statistical analysis.
These are isolated patterns.
Right, exactly. And so the other very interesting thing is we are doing, for example, mass spectroscopy itself has actually advanced tremendously in the last 10 years. We now what are called proton transfer mass spectrometry,
Yeah.
where you can actually do part per trillion molecule detection because you eliminate fragmentation of the molecule when you ionize the molecule, which is the biggest problem in mass spectrometry. We use electron beam to ionize a molecule, but it not only ionizes it, but also fragments it, and therefore you get a pattern and not a single peak, and that reduces the sensitivity. But now we have these proton transfer mass spectrometers, which have just come into the market, and they are, like part per trillion. You can go to that end of the room, you open a wine bottle, the instrument here will go crazy in, ethanol, basically. So we've been deploying this and doing real-time catalysis. We're looking at carbon dioxide and water being reduced by copper, and now we've developed a novel catalyst because we can actually measure the products that are evolving from the catalyst in real time. Conventionally using the spectrometers, it'll take roughly 1 hour to get a data point. Here we do this basically in real time. And therefore, we've developed a very beautiful novel catalyst involving boron and copper. And this catalyst converts CO2 and water into 82% efficiency into ethylene and ethanol. Okay. The market value of ethylene and ethanol is incredibly high compared to So we start by next year. I'll be floating another company. The aim of this is to be a big catalyst machine that will be put in a power company, next to a power company, and at night the company essentially dumps the power. Say, hey, don't dump the power, dump it to our electrolytic machine, and we just pump in CO2 and water, convert it into chemical storage, basically. And so this is another very interesting potential. The last very interesting area is the Agri Veterinary Authority of Singapore has approached me to sign an MOU with them to do this sort of food safety become an issue in Singapore because 95% of the food is imported in Singapore. And last year there were several cases of food recall. There was a listeria poisoning of rock melons and shiploads of Australian things had to be sent back basically. So this is a big issue. And even in the United States, the largest industrial recalls are actually in the food industry, not in the auto industry. So last year we had salmonella in egg, we had E. coli in lettuce, we just a lot of them. So essentially, the nice thing about food is when they go bad, they smell bad. So VOC detectors are really big deal. So low cost, VOC detectors for food safety. Food production is another interesting thing. As you mentioned about beer, essentially you take cheese. The most expensive blue cheese is obtained when the fermentation process is just on the verge of the whole thing turning into a crop, basically. The closer you are to the crop end, the more expensive the cheese is, right? And there's an expert who smells the thing and he says,
it's an organic example of what we say, the boundary between being crazy and being smart is very narrow.
Exactly. And the closer you are to that boundary, the more expensive it gets, right? So that's exactly the thing. So essentially, there's a huge market here for VOC sensors that are low cost. Even at home, right, we sometimes wonder, should I drink this milk or not drink the milk, right? So a sensor that I can dip in, right? It would be very, very cool to have, right? So anyway, this is another, so I kind of see this as a multidisciplinary kind of a center with AI and machine learning coming into this.
Yeah, one comment I want to make.
Yeah.
I know you keep emphasizing pattern recognition, but I think the problem is joint algorithmic design pattern recognition and the sensors.
Yeah.
So then the question is the following. Do you get involved at all in what we call in this country material origami, meaning specifically designed materials that they have specific sensitivity properties to detect some of these single molecules or collection of molecules? Is that work connected to that work here?
I don't know how to answer your question.
Because the new vice president we have, who said, civil scheduling is a fantastic group that exists in English. Working with, which works exactly on trying to tailor material design down at the quantum level,
right? So
that specific properties.
I would say, that part of the material design thing is, significantly further down the road. I would sort of say real what I would call impactful thing will come out of that probably maybe 10 years from now. I don't see, it making an impact at this stage. Like autonomous material
In
design.
university, we already have something which is called light wood, which is a strong, is wood based, but it's as strong as steel.
Right.
In another university, we have transparent steel. So it's not that far away.
No, what I'm trying to say is, for something like food sensors and those sort of stuff, I'm talking about that end of this sort of thing. It's you probably would like to try techniques that you know of, create these. And that's what you
Have you talked to the people here that because we have a food safety center?
in Maryland?
Bill Bentley is involved, yes.
Oh, okay. Yeah, and I spoke to Bill about it. Bill is very excited. He said, come and set something up in our center. He just keep telling me that. Right. Yeah, what is it?
So are VOC sensors needed in the development of novel catalysts?
No. Oh, you mean the novel catalyst?
Yeah. Yeah.
No. Actually, the novel catalyst, the VOC sensor is, if I'm going to convert something into something else, some product, okay, and like for example, in the case of CO2 water, the product most desired are actually ethylene, ethanol, propanol. These are the things. So you can try to optimize for those molecules. So you need a VOC sensor basically that's tuned for those molecules. See what I'm saying?
Yeah.
That's a good point. Okay, so these are some of the companies that I would like to start in the next 10 years. And this year we started these companies, Raponics. So this is my student. So she started this, the breath analysis company. And then we also grow, we've shown that actually cells grow differently on different surfaces. And we've actually developed some oxide surfaces on which stem cells grow about 100% faster than any other surface. So we started a company called Cellivate. This is the first stem cell therapy. Because one of the big issues in stem cell therapy is the time it takes to take the patient's stem cells and converting it into, let's say you have a burn victim, you take the stem cell and you try to make an artificial skin for that person and to put it back on the skin. And there's a very long wait time for the patient. And so if you can reduce it by a factor of 2, that is a big deal. So this is one thing. The other interesting thing is that we have a large number of companies. Now, my problem with all of this is really, starting companies is you need the right person to start the company. So very often when a student comes into your lab and you look at them, they look very academic and tailor-made for university. But I have an instinct for finding out which other kids who can start a company. Who have the, because basically to start a real company, you need kids who don't shoot from the hip, who have a lot of common sense, and who have a vision and are very systematic and can follow through. Good. That's all you really need for them to become an entrepreneur. And they have to have good people skills, basically. That's very important. So essentially, it's I say entrepreneurs are not necessarily born. You can make them. And so I always try to look for students whom I can train to make them. So that's our basic limitation here. Okay. But so that's it. So now I come to the main part of my talk, which is really low energy memories. And I've got to give you some rationale as to why it is needed. Okay. Okay. So here I just took the population of our Earth, and essentially our brain, an average human brain uses about 20 watts. Okay. So I calculated the total energy power consumed by all human thinking activity. It's about roughly this number, but 10 to the 11 watts. Okay. That the whole Earthlings are generating this much power. Of course, there are two crucial assumptions here, which takes the number away. I'm assuming that everyone is awake at the same time. Okay. And second, I have not included the brain power of our beloved leader in the White House. So that would totally offset these numbers, because for him to make any sensible comment would require terawatts of power. So being very energy conscious, he doesn't want to use, he wants a sustainable energy. So he believes in it, so he's not using terawatts of power, and that's the reason why we hear what he says are not quite up to the mark. But anyway, that's different issue. Now, this is the power consumed by data centers in 2016. I mean, just look at the numbers. These are really phenomenal. I mean, this is 2016. By the year, something like 2024, 25, 20% of the global power will be consumed by data centers.
This is a single data center.
Say it again?
That's a single data center?
No. These are total all the data centers.
All the
data centers. And this
This
is
to me is low.
what is
To
it?
me it's low.
It seems low.
That number is low, I think, for all the other things. it's low.
Really?
Yeah.
Okay. All right, let me check that out. I'll check it out. You know, this one? Say it again?
Yeah, but it's low. If you look at one number alone.
This is 2016, not today.
That doesn't include laptops and stuff like that.
Which one?
Doesn't-
No.
Just
This is
send-
just the data centers, right? And by 2025, 20% of the globe, if you continue at this rate, right, by 2040, the world will not produce enough energy. We can't produce enough power to control all the data centers, they provide for data centers.
No, now it's becoming solar power.
I'll say it again?
Now they are becoming solar power.
Yeah, you know, well, so essentially, you know, 50%, and the key part is 50% of the energy consumed in this is actually in the memory. So the memory is a crucial guy. So if you can reduce the memory energy consumption of the memory, it could make a significant impact. Okay, so that's the main message.
There's another example I like very much.
What?
Which you see, right?
Yeah.
When they talk about, you know, the chess competition between Watson and
Yeah.
the world champion,
Yeah.
they say, okay, the Watson beat the world champion, but the energy
Yeah.
that they consumed with all the computers
Right.
is about 4 orders of magnitude higher.
No.
than the brain.
No, not four. It's like, it's 20 watt for the computer genius, and it's terawatt for that computer.
very
It is like, man, it's like, it's
And
a
then you say,
huge.
if you impose the same constraint of power, I will beat him in 2 seconds, right?
Yeah.
Actually, 10
Right.
machines at the same time, they actually will beat them with the same power.
So basically, you know, see, there are several takeaways here. One is, if I can build memories which consume a lot less energy, a lot less power, that would be really great. And second thing is that actually, there's a real need for an alternate device technology, basically, you know. I mean, essentially, our current semiconductor logic is basically Boolean, you know, von Neumann-based logic, and there's no real way to really reduce the energy consumption of these devices. And actually, for example, you know, the IBM has introduced a true NOR chip, and then Intel has introduced the Lowy series of chips and so on. They simulate the, you know, the neuronal functions in some ways, primarily from the point of view of the asynchronous logic and a few other things.
No, they
But-
are different. They can use passive computing.
Yeah.
So the two examples you mentioned,
Mm.
the internet, the IBM one is very high power, the traditional digital logic. The Intel is very interesting because it has analog components and it has impulse-like computing like you do in the neurons, which is extremely interesting.
But-
And for that, they get much lower energy.
But they have artificial synapses.
Yes, so this is why I like it so much. It's the first step in the different direction of computing.
So let me ask you this question. Do you think they have the chance to really bring down the energy consumption by, let's say, 6 to 8 orders of magnitude?
Well, if they continue to pass, because the energy difference between the IBM chip and the Intel is already 2 or 3 orders of magnitude.
Okay. Yeah, true. I mean, what I feel is the reductions would be on the order of, let's say, 2, 3, that sort of thing, not it's like 6 orders. That is the reason why I feel that an alternate device technology is needed. It's like, I mean, if you look at a neuron, it's just like an incredible technology, basically. I mean, the nature's technology. So we have 3 different approaches to designing these things. One is an organic approach, and then an oxide-based approach, and lastly, I'll discuss a little bit about live neuronal approach, which is what we are doing next. And so this is an organic compound that was developed in my laboratory, and I think this molecule is going to become pretty famous very soon. Huh?
What is what you call it?
Okay, it's called RUPAP, and it's essentially a ruthenium-centered 3 ligand molecule. So this is one ligand, another ligand, and the third ligand. And these ligands are the really crucial players is the N double bond N, which is the azo group that is really very important in this molecule. You can just spin this on, you know, and then, so we take an ITO, indium tin oxide, grown on YFZ substrate, it's going to stabilize zirconia substrate. We do this by PLD. And this surface is atomically flat, really very smooth surface. We spin this molecule on, and then we just put some gold electrodes. So the brown thing is the molecule, and then the gold electrode.
How
Then
many
we
layers you have on it?
which one?
How many layers you have on it?
No. The basically bottom electrode is ITO, then you have this molecule, then there's voltage.
What's the thickness of the molecule?
The molecule is typically less than 100 nanometers. It would be of the order of like, typical working numbers are like 50 nanometers, 60 nanometers, something like that.
16?
50 to 60.
Oh, 50.
60 nanometers, okay. So this is the current density versus the voltage for the molecule, and it very clearly, is ohmic here, and at this voltage it just switches up, and then it develops a hysteresis, and then comes back down, and then it goes back up again, and comes back down, and so on. And what this fuzzy line that I'm showing here is essentially the total data of 321 devices of completely different sizes, ranging from 100 microns to 1 micron, and a variety of these devices. All of them are plotted here, and you can sort of see that this cloud are very well separated. That means the on-off ratio is large enough that there's no potential for error in these devices. That means, if effectively you can put a number on it, the potential that you'll have an error when you make these devices is about 10 to the minus 13 or less. So it's really a very good manufacturing process. But what is
Do
really...
you have a manufacturing process for this?
Say it again?
Do you have a manufacturing process for that?
No, I'll come to that towards the end. I'll come to that point. Okay. One of the problems in organic electronics is most devices in organic electronics turn out to be fuses. You turn them on and they go to one state and that's it. Then their devices are pretty much dead after that. But having repeatable devices is very unusual. And secondly, most people in organic electronics don't know why the device does what it does. This molecule is very exceptional in that sense. For example, this is the ligand, and virtually all the charges that are changed in this ligand, which is what happens, the charge state of the ligand changes, which is put into what we call chemistry-wise redox states. Okay, so the Raman spectrum of the molecule is a very beautiful indicator of the charge state of the molecule. So, for example, you see all these are vibrational modes of the other parts of the molecule, but there are three modes here. There's 2, 1, and 0. These three modes correspond to just the azo group. Okay, so when when the azo group has no electrons in it, basically like it's an N double bond N, and then when I essentially add an electron, I get this, and then another electron, and I get this, and essentially when the three Raman modes corresponding to these states are very well defined. This is mode 0, mode 1, mode 2. So by just looking at the Raman, exactly,
If I do quantum control, I can...
Say it again?
I can repeat the cycle, right?
Say it again?
If I do quantum control, meaning I interfere now with external fields to the quantum trajectories of the electrons, I can repeat the cycle.
Yeah. This is completely reproducible, this stuff, basically. So I'll show you I'll show you the data. So here is the actual state of the molecule, the redox state of the molecules at different states. So I start at 1. Now you can see that this is 0, this is 1, and this is 2. Okay.
So the color is different states, or how do you characterize the states here, right?
Okay.
Distribution alone by the color, by what?
Okay. So essentially what it is this line is the actual data,
Right.
and then I'm deconvolving this into two peaks. This one, the yellow is this peak,
Okay.
and blue is this peak. So this yellow corresponds to a molecule in the 0 state, and blue corresponds to a molecule in 1 state. What this is telling you is the blue is 2 times larger than the yellow in the area, and that corresponds to a molecule with 1 ligand in one ligand in the 0 state and 2 ligands in the 1 state.
What's the y-axis?
Pardon?
What is the y-axis?
Here, you mean here?
Intensity?
Here, the Raman count. That's it, Raman intensity.
Okay.
Raman
So
intensity.
this is energy issue?
Which one, Raman? No, essentially, this is the Raman, the wavelength of the Raman tells you the vibrational mode, and then this tells you, the intensity tells you how much of it is there.
So intensity is with respect to physical physical power?
Not power. It basically, what it tells you is that if I had a finite set of molecules, I do a Raman spectrum, then the spectrum that I would get will have a finite area which will be preserved.
Okay.
The area is preserved. So it's going to get distributed among different modes, but I know exactly from the ratio of it, how many molecules are in which mode, basically. You see my point? So you get a very precise number from this. So here, this tells me that this molecule is in 110 state. Now when I apply the voltage, now you see this guy becomes doubled of this, and now this is 1, 0, 0 state. Now when I go to this, once I switch to this position here, you see there's only one peak left. So all the three are in the 0, 0 state. You see? There's actually a very, very beautiful system which tells you what the status of the molecules is. Now when you come to here, in this on state, it's all of them are in the 1, 1, 1 state, and here they're in the 1, 1, 2 state, and then they finally come back down to 1, 1, 0
So
state.
you have an identifier from, in terms of Raman scatter from the states.
Yeah.
My question is, do you have a map from the states to the quantum orbits?
Yeah, well,
the electrons of the atoms that they make them work.
Yeah. We have essentially a quantum mechanical model for this thing that will describe all the stuff. So the theoretical stuff with which you can calculate all of these, we calculate the energy levels, all of this.
Right.
So the point here is, what happens is the energy levels for a ligand within the one state, for example, are slightly shifted from that in the 0 state. So as a result, the reason why we get these off and on states are because of the Hall effect. So you can sort of see the so-called on state, where the resistivity is lowest, is where all the ligands are in the same state, okay? And that is because when the ligands are in a different state, it's difficult for an electron to jump, yeah.
Yeah, when you were discussing the state of the molecules,
Yeah.
these are ensemble of molecules?
These are?
These are ensemble.
Yeah.
Or just not a single molecule, these are
No.
ensemble.
This
So
is
all the
they're
molecules are
spun on,
prepared-
right? So it's actually an ensemble of molecules.
So all the molecules are prepared in the same state?
Right,
There are
right,
not
right.
some that are in different states?
Well, you see, if for example, when I have 1, 0, 0, it means that every molecule is in the 1, 0, 0 state, basically. You know?
All of them?
Yeah, all of them tend to be in the same state, basically. And what is interesting is, let us take, for example, why is it in the highly conductive state, all the molecules are in the same redox state? For example, 0, 0, 0 is an on state. Here, 1, 1, 1 is an on state. And the reason for that is because the electrons are actually hopping from molecule to molecule. So they would take roughly about 40 hops before they get from the bottom electrode to the top electrode, okay? Okay, let us just say if the molecules are all in the same state, then what happens is, let's say the probability that the electron hopping from one molecule to another molecule is 1, okay? But if the molecules are 1, 0, 0, now you see there's one state is different, and therefore the probability of hopping in this case would be roughly 2/3 instead of 1, because you know one of the ligand hopping would be forbidden, right? But 2/3, you know, you have to do it 40 times. 2/3 to the power of 40 is a very small number, basically. That is why this is an off state, basically. So this guy is different from here in terms of conductivity by roughly 2 to 3 orders of magnitude because of this difference, basically. You see what I'm saying? So that is how this whole principle of why this molecule works the way it does. There's another very interesting, why do I feel that this molecular system is ideal for building neurons? There's a lot of knobs we can tweak in this molecule. There are what I call, this is a central molecule which I showed you, but there are these so-called counter ions, there's 2 counter ions, which sort of go along with this to maintain charge neutrality. And these counter ions do all kinds of cool things. So, for example, when the redox state changes, the counter ion just moves to a different pocket in space next to this molecule. And
That's the ruthenium one, the orange one is the ruthenium?
yeah, ruthenium is here, right here.
And you have only
This is actually phosphorus,
blue ones,
it's a PF6 molecule, basically.
Oh,
Okay,
okay.
it's a counter ion, basically. And these counter ions, actually, they hang around next to this molecule, and they're in very specific pockets in space, actually, next to this molecule. So what happens is, the moment I switch them on to this state, the counter ions shift a little bit in space. And what happens is that they give inertia. So when I turn the voltage down, the counter ion hangs in where it is, and therefore it doesn't completely switch off right away here. And I show here, for example, 3 different counter ions. Light guy like chlorine, PF6, you see they're very good inertia. But then when I go to a heavy counter ion like BPH4, it just cuts off much more easily. So this is a very important aspect of it, because when we design what I call devices called selectors that are used in crossbar switches, this fact that we can tailor this hysteresis becomes very important, actually. and I'll come to that a little later. Okay. So anyway, when we first, we were very excited about this paper. We submitted it to Nature, and we went through 3 referee processes. Unfortunately, with the third one, they said, well, your switching voltage is too high. We don't see how you're going to scale it down to small devices, and switching speeds are microsecond, energy inefficient, blah, blah, blah. So we started then looking at least what are the solutions, what can we do? So we started studying the current evolution and seeing whether can we enhance the behavior of the device using higher electrical field in the devices. So essentially, this is the device geometry that we've been exploring so far. So we started putting gold nanoparticles on top of the indium tin oxide. So these are sputtered gold nanoparticles. And then this is the geometry. And then in this particular case, we go with the top electrode, which is a conducting AFM tip, so that this is really the most spatially confined device, basically. See, when you do that, you see an interesting thing happen. So, for example, when I take the CAFM of the gold nanoparticles, what you find is the switching voltage is already dropped down to 0.4 volts instead of 4 volts. And then when I start
10 times lower.
you got 10 times lower, basically, because of field enhancement. And you can sort of see that. So when I scan over the surface, you can sort of see when you reach about 0.12 volt, already on top of the tips of the gold are all turning on. So this one has already turned on completely, this device. And then slowly, more and more of the stuff of gold are turning on, and the space in between also starts turning on, and eventually the area gets filled up, basically. So this gave us a really good idea that actually local field enhancement will really help,
Okay, so since you have, sorry, can you go back to the slide? Since you have local field enhancement,
Yeah.
does that mean each point of the gold particles can have a different state? If you have a dense enough array of electrodes on top?
Yeah.
So if you have like a small electrode for each column, I guess,
Right.
of material,
Right,
does
right.
that column material can that column material represent a different state than the next column?
Exactly. You're right. Exactly right. Exactly right. That's what is happening here. Actually. In other words, the smaller the volume.
So you don't need to photo pattern the actual organic molecule into
Yeah.
like an array.
Yeah. We have not done any patterning at all here. It's just a
Ah.
gold nanoparticle, basically. And the film is just spun on top of it, basically. And different parts of the films are turning on at different distinct voltage here, right? So one way, the beautiful thing about Raman is, right, you can do what are called surface enhanced Raman versus normal Raman. So when you do surface enhanced Raman, okay, the way we do it is, this is the resonance of a gold nanoparticle, the absorption profile of a gold nanoparticle. You can sort of see around like 630 nanometers, you're really absorbing very strongly by the gold nanoparticle. Whereas you're down here like 450, something like that, you're a lot less absorptive. So when you do a Raman excitation with a wavelength here, around 450, you will get Raman profile, which is, this is a Raman spectrum, which is not enhanced in any way. And this Raman profile comes from the entire thickness of the film. Basically, the entire thickness of the film is contributing to the Raman data here. Whereas, if I go to 630 nanometers, then what happens is you see the Raman signal is enhanced by orders of magnitude. But now, all the signal is really coming from the molecules which are very close to the gold electrode, because the gold absorbing the photon is enhancing the locally the Raman effect. Okay? So this is a very beautiful technique to find out what is the behavior of the molecule very close to the metal electrode and far away from the metal electrode. And so now we can look at the actual switching of the device. And this is basically one Raman wavelength, and this is the other Raman frequency. And you will sort of see when a switching occurs when this one goes from here to here. So now I've changed, this is the voltage on this axis, and as I'm increasing the voltage, you can sort of see roughly at about 0.6, 0.7 volt, I'm switching from this mode to this mode completely, from here to here. And that's what the device actually shows. Roughly, there's an order of magnitude reduction in the device. And so this is basically this is the overall film, but its switching voltage is reduced significantly because of the fact that I have locally enhanced the field using the gold nanoparticle. But now let's go to the surge mode, surface enhanced Raman mode. Now you see something which is spectacular, and that is this Raman mode. Now you can see the scale now. This is 0.05. So by 50 millivolts, 50 to 60 millivolts, I'm switching from this Raman mode to this Raman mode. That tells you that this device can be switched with a very, very low voltage switch. And sure enough, you look at the CAFM data, And this device is switching now with roughly about a little like 120 million, basically. Just really a very, very amazing device, basically. So this tells you the potential of this
How
device.
repeatable is that?
Say again?
How repeatable is this?
Very, very repeatable. I am going to come to that.
Because that's important, right?
Very important. I'm going to show you what I call the robustness of the data and the repeatability. I'm going to come to that point.
Cycles of switching up and down for 10,000, 50,000.
Not 50,000. This is a problem.
Because if you're going to use it as memory, it's going to need to be.
I'm going to come to the data in a minute. I'm just going to show you.
Yeah.
You're asking all the good questions.
That's the major problem that we have with all these things, right?
Well, I mean, even your, USB 10 to the 6, basic flash memory is about 10 to the 6 cycles, right? And it's not guaranteed
You're
beyond
trying to
that.
replace RAM.
What is it?
You're trying to replace RAM, right?
This would be, yeah, exactly right, yeah. So the interesting thing is, so this is what the data now looks like. You see, if I had very large electrodes, this is the data. But when I start
What's the
shrinking,
lattice?
huh?
What's the lattice here?
Say a micron,
How many?
micron by micron.
Micro by micro.
It's large, so you get like a 4 volts. But now, when I get to a smaller, it's hard to say what the area in this is because one end is the gold nanoparticle, the other end is a 1 micron electrode. But you can already see when I'm actually making the other guy very small, it's already brought down by an order of magnitude. And now, this is essentially a 50 nanometer square. This is a CAFM tip on a gold nanoparticle. And you can see that this is really switching on to this thing. So this is very beautiful in a way because as I make my device smaller and smaller, the device is actually, becoming even more efficient. It's perfectly what we want, in fact. And now you ask all the questions about robustness. How robust are these devices? So you can sort of see, this is a large number of devices, like 300, 400 devices. Basically, they're on currents, off current distributions, and you can sort of see that these are, extremely well separated from each other, and which tells you that if you manufacture these devices, the chance of errors are very low. This is actually the rise time measurement, and this is a very crude measurement done on a twisted wire, not even like a, to really measure the rise time, we need to use, a waveguide type of geometry and essentially get matched resistors and all the stuff. So my belief is that we're measuring a rise time of 30 nanoseconds, but in reality, I think this is at least 1 to 2 orders of magnitude smaller, should be smaller. Yeah?
You indicated before the switching time was 1 microsecond, now here.
This is in the small devices, basically.
The smaller
devices,
devices,
yeah.
you see the 30 nanosecond.
Right,
You're saying
yeah.
it can be even smaller?
Yeah, I think these are like sub-nanosecond switching speeds actually, based on what I estimate for the capacitance and so on. The device should be switching much faster than this. And this is a question that John asked earlier, like how many cycles can you do? So this is about where this is how far you would come with let's say flash memory, and this stuff goes on 6 orders of magnitude better than flash memory. So it's a 10 to the 12 cycles. It just can go on and on. This is actually temperature-dependent data. The device is now operated at 350 Kelvin, and you put it in an off state or on state, and these states are stable. This is effectively about 3 months, essentially, in terms of time. So they're working from minus 40 C to 80 degrees centigrade. And if I calculate the switching energy of this device, basically, it comes to about 36 accuracy.
And the switching level, is different level. Why is that?
Say again?
The level, for instance, on the left.
Oh, you mean that? No, that is because there are basically this particular data would be, you're going on probably the negative side of it, on the other side of it, so the levels may not be exactly the same this side and that side.
The positive side and the negative side are not kind of like symmetric.
They're not exactly lined up, and therefore you get like, principally you can call it a different state in some sense, but it's okay.
But can you use both sides
You could.
for separate, let's say,
You
functions?
could use them, yeah, you could use both sides if you want. Okay. I just thought, so I got very excited. I called up my friends at Intel and said, hey, can you guys give me the roadmap for memristors? What's the state of the art? So this is essentially the answer that I got back is basically that after 2015, they stopped making ideas of the roadmap, basically. And I think no one has any clue in terms of which way the industry is really going to go, basically. We have the Moore's law thing. But he said we had the data for 2015, and so I took those numbers for the memristors. The recurrent ITRF projection should be greater than 10 nanoamp. We can actually do 1 million in current recurrent. I mean, you can, what it really means, you can always design the device to a lower current, but higher current is hard to do. And the best organic device, to our knowledge, is 200 femtoamp at 400 nanometers squared. Right erase time, nanosecond, we are right now less than 30 nanosecond, but I generally think we have not done the right measurement yet. This number is less than nanosecond, I think. Okay, write cycle, greater than 10, we're doing greater than 10 to the 12, and write voltage, less than 0.6, we're doing 0.15, read voltage should be 0.2, and we are less than, essentially 50 millivolts. Write energy should be less than 1 picojoule, we're already 36 attitudes. This is assuming 30 nanosecond write time. If this write time was not 30 nanosecond, but 3 nanosecond even, this would be at 3.6 attitude. It's really ridiculously low energy, basically. So, what's very interesting is
the difference is 6 orders of magnitude
Pardon?
between the pico and the.
That's what I mean.
6 orders of magnitude.
You won't believe it. I'm in the radar screen of guess who? Huawei. I've got a whole team of people from Huawei been writing to me.
When you travel.
Read this paper, they say, we want to come and visit your lab, we want to meet with you, can you please send us your slide? We want to have a.
Good lawyers?
What is it?
You're a good lawyer.
I have decided I'm not going to respond to these emails. I'm not responding to any of these emails. I'm just keeping quiet about it.
How easy was it to make the molecule?
Say it again.
How easy was it? How easy is it to produce this
Okay.
path?
Well, okay. The story behind the molecule is very interesting because this molecule was discovered by my graduate student. It was really, I was this incredibly brilliant student, and it was just like he's winning every awards everywhere. Like the MRS Awards, Europe, United States, wherever he goes and gives a talk, he wins these awards. And he invented this. His molecule was really made by his dad. His dad, 30 years ago, for his PhD thesis, made this molecule. And he's been using this molecule because the beautiful thing about the azo group is you can change the charge state by 3 times. So with the 3 ligands in the thing, right, basically you can change the overall charge state of the molecule by a very large number, which is of great interest in many things like catalysis and many other processes, where charge redox state can be changed. So he's been studying all of this stuff, and the student started doing electrical devices with these molecules. And he showed me all this data, and this like pretty amazing stuff. In fact, the crazy thing is, this student, when he joined the NUS, I got to tell you another story. He went to work for the top chemistry professor in the university. He said, who's the best chemist on the campus? And they said, oh, you go to so-and-so. I'm not going to name that person. But anyway, so went to work with that professor. And that professor basically told this student that, no, you're not going to work on anything else. I'm going to tell you what to do, and you're going to do what I tell you to do. So this student was very convinced that the molecule would be very important. And so every week he'll pipe up and say, I want to tell you about this very interesting molecule. And the professor will say, I am a professor, you're a student, the information flows this way, okay? Made it very clear, So this student got frustrated. At one point he decided
The information or the direction?
What is it?
The information or the direction?
No, the direction. What to do comes with the professor to the student. You don't tell me what you want to do, I tell you what to do. So the student got very frustrated. It's a very independent kid, so he decided at some point he's going to quit NUS and he's going to go. But his roommate happened to be my student. And he said, why don't you go talk to Venky? He was very open-minded about it. So this student came and talked to me and he said, I said, let's sit down, let's talk your data. And he started showing me some initial data and my jaw dropped. I said, holy Toledo, this stuff may be very important. I told the student, man, you're a godsend gift to me. Come, work with me. Yeah, that's it. That's it. So it's literally been an incredible journey after that. And this molecule is very, very exciting in so many ways. I'll tell you. For example, now from the neuromorphic point of view, why are these things important? And also things like crossbars. So this is the semi-log plot, right? But this is what it really looks like in a linear plot, basically. So you can sort of see this kind of a devices are what are called selector devices, which are used in crossbar switches. And I'll tell you why you need them, because See, for example, this is a typical crossbar with various elements, memristor elements in them, right? When you send a current down this line, let's say you look at this device, you get a current going down this way, but then part of the current goes down to this device, which is also on, and it can go down this way, and then it can come up through the device and come back here. And this is called a sneak path, and this is a real problem. So what they do is to get around the sneak path, to each of the device you add an extra diode, basically. So that sort of prevents the sneak path, basically, which is an extra fabrication, another deal. In fact, when people use memristors, what they do is they take two oppositely poled memristors elements. So each one memristor element goes like this, the other one goes slightly the opposite direction.
Right.
And when you combine the two of them, you get something that looks like this, and this is essentially a limiter, which means that you don't get any current unless it exceeds a certain threshold.
W stereotypes.
Yeah. So
W stereotypes.
exactly. Yeah, definitely. So you see, in our case, we are making this naturally, one molecule, single molecule produces. The other interesting thing is, by substituting ruthenium with iron or cobalt, I completely change the profile of this stuff. So you can literally change the profile of this, as well as playing with the counter ions. I can also change the width of the hysteresis loop. So you get all these beautiful ways to tune the molecules to exactly the kind of device you want to make, right? So this is why I think it's going to be very important. Now we talk about
How
neurons.
stable is the
What is it?
How stable is the chemical?
Basic chemical. This is the problem. It's very interesting, right? We take this molecule, we take this device, we take this device in vacuum. I take this device and I heat it up to 600 Kelvin.
I don't want it in vacuum, I want it in regular environment.
In air, it's stable up to 80 centigrade.
Okay.
But in vacuum, it's very stable.
In vacuum, it's very stable. It goes up to 600. I can vacuum and can take
I'm
it.
not interested in vacuum.
No. The reason why it's important in vacuum is because I deposit things in vacuum, you see. So it's very
This is
useful.
not vacuum, okay?
Huh?
Yeah, but you can package things into
No, exactly, that's the point. So you can put like a, like a passivation layer, various other thing in vacuum, and we heated it up to 600 Kelvin in vacuum and bring it back down, and the device works exactly the same it does. But the room temperature, if you're operating in ambient condition, 80 C is the highest temperature you
That's
can go.
temperature.
Yeah.
You're going 600K and you're giving in Celsius after that, so the numbers look bigger.
No, temperature is fine, but.
It's
I mean, what I mean is, like, 250, something like,
Yeah, so
about 330,
30.
I didn't know why you were
centigrade.
switching.
330 centigrade versus, let's say, 80 centigrade in the thing. So, the problem with this material is its sensitivity to fluids, essentially. It doesn't like water, it doesn't like but in toluene it's okay. So what we need is, my biggest problem right now is we are working with a guy named Aaron Thean, who came from IMEC to NUS. He set up a big fab and working on trying to make a crossbar switch. And the problem right now is, how do I do lift-off metallization on top and so on, right? So that's really turning into a little bit of a difficulty, and we're trying to come up with ways to do that. You need an orthogonal resist, basically.
Here is another question. Tell me, you consider, usually when you try to make devices with organic and inorganic materials,
Right.
you have all kinds of problems with interfaces.
It is an issue, yeah.
Here you don't?
No, I mean, look at the metals and all the stuff. We're using conventional tools. We've tried a variety of other metals and they all work fine, no problem. That's not an issue. The issue is in how do we do subsequent patterning steps on top of the stuff. That's where we are stuck at. So right now, one idea we have now come up with is a dual Damascene process where you pre-pattern your substrate and put all the molecules. The molecule kind of fills in these different things, and then you put, say, tungsten or whatever the metal on top of it, and then you do CMP, like they do in the Damascene processes. So that's one idea we're going to be working on to start with. But I'm also working with his dad, who's a chemist, to figure out some alternate etching scheme where we use some solvent that does not affect these molecules, but with which we can develop a resist process, okay? Now, I want to come to the neuron issue, basically. So you see, this is a historical view of neuroscience, right, and machine learning, okay? The neuroscience being started like in the 1940s, Pavlov and various other guys, and machine learning is more recent. But the problem is, you see, this neurobiologists keep working in this line, then guys like who are working on artificial neural nets, like, you know, Hopkins, there is all the other people, Hopfield and all, they're all in this line. Then you have statistical machine learning, dynamical machine learning. The interaction between these various paths are very, very limited, basically. You know, that I think is a big, you know, thing that needs to be really, in my opinion, a strong interdisciplinary collaboration is absolutely essential.
But they don't compact.
Say again?
People don't try to compact knowledge in this whole thing.
They don't. I mean, I'll give you
And the example I give is the expanding universe, because you get a big bang and then the world is arrayed, right? And then there's a theorem that says if you do that, you're going to collapse under your own gravitational.
Exactly.
And that's happening.
So, you know, I mean, when you look at the neuron and you think to yourself, like, you know, you mean Taiyu light or whatever this, you know, the supercomputer, you know, compared to anything else, right? I mean, to me, the neuron represents true technology. I mean, it's like, I mean, this is truly amazing. I mean, like the axon and the way the soma processes the signal and all the dendrites coming in information in. It is truly amazing. For example, spikes. I mean, today, you know, there's still debates as to, you know, the neurons deal with spikes and not digital pulses. But, you know, up until now, neurobiologists always said a spike is a bit, you know. But now people are questioning it, you know, is a spike a packet rather than not a bit, you know. So that raises some interesting issues, like our brain is supposed to process like 10 to the 16 or 10 to the 18 spikes, right? I mean, that's our brain processing thing. But if a spike is a 10 to the 4 bit, then we are really processing information like, you know, over 10 to the 20 to 10 to the 22. It's really humongous rate at which our brain is processing information. It's really amazing. And asynchronous is no three-terminal device. We have 10 to the 4 input to a neuron. A neuron is from that many dendrites, you know. And you try to design a circuit. I mean, the maximum we can do is about 6 interconnects. At least 2 are already on for power in, power out. So you get 4 interconnects. The axon is a lossless transmission line, literally. And the signal along the dendrite is dynamically processed, not a simple wire. And a lot of the signal processing in the brain is very close to chaos. In fact, you don't want coherence in the brain, you know, that will lead to epilepsy, you know. So, you know, you don't want coherence in the brain. And
You don't want to coherence in the internet either. Right? If all the things synchronize, you're dead. This has happened many times.
yeah.
Okay, so a comment about the asynchronous pulses. I'm taking neurobiology class right now,
Yeah.
and the spike pulses are asynchronous, but they're correlated with frequency. So intensity is coded into the frequency of the spikes.
Yeah, it's more in the time domain.
Yeah.
Yeah, no, I mean, I'll be honest with you, I mean, a lot of this stuff, I'm at a very beginning stage of learning all of these things myself. You know, you can't be an expert in this field overnight.
Right.
But on the other hand, our focus is more on the device end to see how can we build things that resemble the stuff. But I think the way the field needs to evolve is bring in people who think about these issues, like spike logic and those sort of stuff, and start working with them, right? And, you know, so for example, right, the role of negative differential resistance has been, you know, sort of like, so one of the first guys to emphasize this is Leon Schwab, and this was essentially the Hodgkin-Huxley model developed in 1952, and essentially they took this giant squid neuron, which is a fairly large neuron actually, like a fraction of a millimeter in diameter, so you can actually pick it up and you can do experiments with it. And that's how they developed this model for the neuron, essentially. These variable resistors have some sodium and potassium channel. And this model has remained unchanged since 1952. You know, this tells you the interaction between these fields is so low. I mean, can you imagine any physics or an electrical engineering concept that has remained untouched for 50 years? I mean, I can't think of anything. Almost everything gets, you know, modified in some way, you know, into like what?
Look at what we teach in communication theory, right?
Yeah.
It hasn't changed for 40 years, right?
Hasn't changed for 40 years?
Yeah, nothing. Everybody still thinks that everything has to be measured in terms of bits.
Oh, yeah.
My claim is bits are irrelevant for this model, but that's another story. And NIH has come here and challenged us to develop a communication theory for biological systems, right? Because,
Right.
as you know very well, all the communications there are chemical, which means they're not in terms of physics, they're in terms of chemistry and geometry. We're nothing like that.
Yeah.
And we try to mimic it by resistors and all that stuff, because that's what we understand. Sometimes it works, sometimes it doesn't work. And we have to move away from this discretization of everything, right?
Yeah.
See.
Well, I mean, the cool thing is that the Chua basically replaced these guys with memristors with negative differential resistance, and that would really make a big difference. So, for example, there's a Hewlett Packard data on a negative differential resistance device based on iodine oxide, and you can sort of see when you're below threshold, above threshold, you can get a very nice walking output. Below threshold, it's really small output. So this kind of would be one way to develop what I call the equivalent of an axon, because it's like having a gain in the system, right? So you can account for the losses along the line. So what I would say is, for example, in our molecule, this particular molecule, in the negative side of it, we actually see a region with a negative differential resistance. You see the bistable values of the current density versus voltage here. And similarly, there's a slightly different molecule in which we actually see very beautiful, negative differential resistance. So this molecule has that aspect of it also, which is very important. Then we can generate a ternary memory using a slightly different molecule, and this gives you a very interesting opportunity. There are three memory states here, here, and here, and this particular memory state arises from something called charge disproportionation, which wouldn't have no effect on you, but if I show this to a chemist, they will salivate like crazy, because for them, charge disproportionation is a very, very exciting, chemical phenomenon. And so this is the non-charge disproportionate state, and this is the voltage-driven charge disproportionate state. And so this is one of the first examples of a voltage-driven charge disproportionate state. What it does is it ends up creating what I call supramolecular dipole, as a result of which the capacitance of this device exhibits tremendous memory characteristics. So this is a mem capacitance, and this is a memristor. Okay, so the memristor, mem capacitor here, which is a very, very unique thing in this system. The other interesting things are, at a certain temperature range, this molecule exhibits multiple states, basically. And you see, this is a 16 nanometer film, okay? You divide 16 nanometer by the 3 steps that I see, I get 16 divided by 3, about 5 nanometers. Okay, 43 nanometer film, I get 8 steps, 43 over 8, again, around 5 plus minus that. Now 64 divided by 12 states, again 5 nanometers. So what is
Are the states equally well discriminated?
Pardon?
Are the states equally well discriminated?
You can see there are.
Because they get denser and denser. If you look at the last one,
Yeah.
they're not as well discriminated as before, right?
What do you mean they're not well discriminated?
I mean,
Separated.
One of the things separated. One of the
Ah,
things,
you mean the separation.
one of the things you worry is some time electron does something and it keeps you switching states all the time, right? Or
Yeah.
something like that. So
I mean, look, there are a lot of things that are problems with this in the sense that to observe these, you have to scan at a particular time frame. If you scan too quickly, it goes away. If you scan too slowly, it goes away. But there's a certain frequency at which you see all these steps showing up.
But what do you
So whether I can use it or not is a different
why do you
issue.
want to go to more states?
What is it?
Why do you want to go to more states?
No. What I heard from people is having discrete states in the molecule is
Fine.
No, but I'm going to, my excitement right now is because how to explain this data, there's a very interesting thing that's going on in the system. To explain this data, essentially, 3 steps means, what it means is, this 5 nanometers is roughly 3 times the molecular size. The molecule is 1.5 nanometers, okay?
Right.
So 3 times that is about 4.5 nanometers. What it's telling us is that 3 molecules are switching simultaneously in the system. See, that's what excites me, not the application or anything. But scientifically, I'm spinning on this molecule, right? How can this molecule, basically, it's self-aligning itself in the on state. Once it's in the on state, the molecules are all self-aligned. I mean, really, such that the top layer next to the metal electrode, I can switch those 3 guys off, the next 3 guys off, the next 3 guys. Why this 3? It's because, then we said, the counter ion, the PF6 is a big counter ion. What if I replace the counter ion with a smaller counter ion, like fluorine? Will I be able to switch just one monolayer, right? Okay, that was the next question. And that's what we did. We replaced the counter ion with chlorine. And now you see, a 12 nanometer film gives you 8 steps, which 12 divided by 8 is 1.5, right? That's exactly a single molecule that I'm switching. I mean, I've never in my life seen something like this. What I would expect a system to be amorphous can exhibit a phenomenon like this. It just blows my mind, basically. You know? So this, I think, and here, a 44 nanometer film gives you 29 steps. You can actually count them all exactly, and that's what you would expect for a 1.5 nanometer molecule size. So this molecular system is amazing. The other interesting thing is it also produces optical signals. For example, this is the optical absorption spectrum, and this is the photoluminescence from it. And the photoluminescence depends on whether the substrate is N-type or P-type. If the substrate is P-type, the photoluminescence signal is very weak. In the N-type, the photoluminescence signal is very, very large. And so what my student did is we took a graphene, whose charge state can be polarized from P to N, and we put like SiO2 and silicon. If we bias this whole thing, the surface of graphene can now go from P to N, and then see what happens to the photoluminescence. So this is essentially in the P zone on the graphene, and you vary the temperature from 7 Kelvin to room temperature. The photoluminescence signal is very broad, hardly anything changes. But whereas if you look at on the N zone, basically N-type zone, the signal just changes by several orders of magnitude, and it also shortens up like crazy. And so this is this kind of a spectrum that you get, like a sporadic kind of curve that you get. And this is, you see that photoluminescence change by like 3 orders of magnitude here. Now this is very important because one of the things people do in brain studies are what are called photogenesis, which is the way to get, you know, when the device switches on and off, the neurons produce light basically because they take it, and the calcium concentration changes, it causes essentially you can put a molecule that it will fluoresce basically, and that's how they can study. So you have an automatic photogenetic capability in these molecules, which I think is interesting. So of course you have to make this mandatory, you know, organizational image and all that stuff. So this is actually an entire device where these regions are turned off. The off regions all light up. These on regions are all black in this case. You know. The material is also piezoelectric, it turns out, and it exhibits about 7% piezoelectricity. It's one of the largest known piezoelectric effectors in the molecule. It's because when the molecules charge up, right, they separate, basically, you know, and that's what gives you that stuff. Okay. We also doing oxide-based memory store approach, but we use what are called tunneling electroresistance capability. So I'm not going to cut my talk really short quickly because I know I'm overgoing. So here, for example, a tunnel resistance junction is made with you have a conductor. You have a substrate on which you grow bottom electrode, then barium titanate is a ferroelectric, and then you have a top metal layer, basically. And if you look at the tunneling characteristic of this, the resistance looks like this. It shows this, you know, orders of magnitude on-off ratio here, as you see. So we studied this very carefully. We created different types of tunnel junctions. This substrate is conducting it. Now you're going to do structure titanate, barium titanate, platinum, then we insert extra layers in between, you know, to see what is that. And these are all basically single crystal structures, as you can see here with DEM. And the interesting thing is that as I increase the number of layers in between, the on-off ratio keeps on increasing. So you can get like 10 to the 5 on-off ratio or 10 to the 2, and you know, all that by varying the number of layers. However number of layers I put, the switching voltage is purely determined by the ferroelectric. It completely is independent of what layers I own on either side of it. So you can see all the 3 cases, the coercive voltage is the same, saturation voltage is unchanged, basically. So what really happens is that, you know, when I increase the number of layers, essentially this is the on-state resistance. The on-state resistance increases much more slowly compared to the off-state resistance, which increases much more rapidly. You know. That's why you get this very large on-off ratio. And you know, you can't, the bottom line is, technologically, you don't need 10 to the 5. You know, what you really want is an RC time constant, and RC time constant is really short. So you want to keep this R really low. And so that's the thing. One of the things is, now the question is, how many unit cells of ferroelectric can we use as a battery? Here I'm actually showing that the ferroelectric tunnel junction works up to 2 unit cells. Actually. We can go down to about 2 unit cells, like as shown here, and it still works. I mean, you get a ferroelectric loop that uses it. And now we've actually, we've now shown that using 1 single unit cell of ferroelectric, we can make a tunnel junction, which is amazing. Because theorists have always been saying that for a ferroelectric to exist, it must have a minimum of 3 unit cells because it needs to know which is up and down. You know, 1 unit cell can't tell, you know, but turns out it's not correct. One unit cell ferroelectric can exist. That's what we proved basically. Now what we do, in a conventional auction members, auction vacancy motion becomes important. So this is the kind of characteristic you can get with, this is a tunneling ferroelectric tunnel junction. This is actually a membrane behavior arising from auction vacancy motion. So you can see now you can create multi-state devices with this sort of behavior. So these are the 2 knobs we can tweak in the case of oxide-based devices for eventually trying to make neuronal type circuits. Okay. Now I'm going to just go to the light neuronal approach. And this is very interesting because we create a variety of oxide libraries on surfaces using pulse laser deposition process, and you can create a library. So for example, this library will consist of zirconium oxide here, yttrium oxide here, you know, say manganese oxide. So now we can create like a ternary, quaternary phase diagrams all on a sheet, and then you can grow cells on top of it to see how do they behave and so on. Okay, and quickly with that, we do a lot of studies like weighting study, water contact angle, surface roughness, just to make sure that all the other factors are not really playing a role. And it's really from the surface chemistry is what matters. Okay? This is the data really important for you to look at. So this is a binary library, yttrium oxide on this side, zirconium oxide in this side. And I'm growing a neuronal crest cell. Okay? So you can see what happens. The cells don't grow on the yttrium oxide side at all. When you reach about 10% of zirconia, boom, they start growing like crazy here. Similarly, on the other hand, fibroblasts, this is a muscle cell basically. And this guy starts growing at roughly around 50% point, and then it in fact exceeds the control. That means it's better than, say, class 5. Whereas keratinocytes do something different. They don't show the, like what I call a step function, but like more like a gradual thing. What we've actually shown is,
do the cells grow independently, or do they just grab any material with the growth?
no, when they grow, they need to adhere to a surface. They need to adhere to a surface. There are different types of cells. All the cells that I showed, they need to adhere before they can proliferate. Okay? There are some cells which actually grow in a fluid medium, but roughly only about 20% of the cells are of that type that can just grow in a liquid medium. Most cells would need, like artificial meat, everything, all those cells have to grow on the surface like this. And essentially, we've come up with an equation, single equation to describe a cell surface interaction, and it really depends upon 3 parameters: beta, which represents an enhancement factor, gamma, which represents the impediment factor, and the critical concentration of, say, let's say zirconia with respect to yttrium, for example. So we can actually now start describing these interactions. I kind of feel like we kind of started a new field here in terms of cell surface interactions here, and this is the kind of stuff that we can calculate these parameters and start developing it. Yes.
There's no other surface treatment other than yttrium or zirconium.
Yeah, exactly. But you can actually put things like fibronectin. People put an organic coating like fibronectin and all the stuff. But even if you do all the stuff, still the surface chemistry actually dominates, which is very interesting, really. And for example, they use a variety of organic coatings to essentially enhance adhesion and so on. In spite of all of that stuff, these factors actually work, basically. But these data are shown without any organic coating. These are the direct cell interaction, which is very interesting. But for example, a lot of the cancer cells, like yttrium, not the zirconium. Now what is beautiful about this stuff is now, imagine that. So we started this company called Cellivate because when we take a stem cell, a neuronal stem cell, right? This stuff, when we grow it on top of zirconium oxide, we grow like 200% faster, essentially, really double the speed with the growth. Which means the surface really plays a role in terms of the thing. So for example, artificial meat, one of the big issues is the price is determined by how quickly you can grow the cells. So essentially, these type of surfaces could be very, very useful for that sort of thing. So I mean, we've just basically compared like a couple of molecules, really, with the whole periodic table is there, so we don't know what all you do. We have developed antibacterial coatings using the similar kind of techniques, and so on. So it's a very rich field. So now, my big ambition is we want to grow real-life neuronal circuits, basically. What I want to do is to put say a 7 by 7 or 5 by 5 neuron, and how will this circuit function? That's what I'm going to do. So there are companies like, they're actually working on these sort of things. Here's a company called Neurosyntech in California. We are actually collaborating with Neurosyntech and then the Yale System Biology Center and us to essentially try to make, this is actually a CMOS chip underneath, and these are metal electrodes that poke out. And their problem right now is when they grow the neuronal cells, you can sort of see them just totally randomly growing everywhere. See, they have no control. They can't get the neuron to sit right on top of the metal, all this sort of stuff. With our coatings now, we can essentially tell the neuron where to sit, basically. See, because we can put on top of the entire circuit the surface which inhibits coating. And wherever we want to enhance a coating, we put that right over the metal and we put the stuff. And the cell will grow right there. Then the axon loves to grow in a groove. If you graphically make the groove, the axon will go only along the groove. So the cell will orient itself so that the axon goes along the groove. And we can actually create live neuronal circuit. So this is my dream, to make a live neuronal circuit. The idea is we will really understand how neurons really communicate with each other with a more systematized kind of a device. And the dendrites, of course, you can't control because it's just too many of them, right? But you can use a laser beam and you can cut the dendrites off. So you can actually tailor the dendrites as you want.
Has anybody shown in all these companies or your own work any initial work along the following question? Can I show neurons and dendrites grow in response to need?
Response to?
Need.
Need.
For instance, with that, I was doing experiments in simulation where I think of a collection of neurons in the computer, and I give it data, very, very simple abstractions, and I ask it to compute it. All right, so now I allow every node to have some very simple computational capabilities, and I allow it to lead to other neurons. Because the big question here is, okay, neural networks grow partly because of reprogrammed via DNA and all that, and also by response to need. Right? And the theory is that the more primitive the animal is, like a meat and so on and so forth, the more everything goes programmed. The more advanced the animal is and needs to interact with the environment, then the two things come to balance. This is one of the big unknowns, puzzles in biology, right?
No, I agree.
So you have those to control it. Can you close the loop and make sure the control is the response to some need? That's what I'm trying to ask.
Well, I'm actually looking at things even more basic than that. I would like to, for example, take such a circuit and really understand how, let's say, you stimulate the first neuron. See, how does the signal generate subsequent signals along the neurons? How does it propagate, for example, down the chain? I would like to come up with some kind of an excitation protocol which gives me a final output of the circuit, which will be like what I call a figure of merit. So my question is, can such circuits be built with the figure of merit having a very small standard deviation, so I can actually say, have some control, on how I'm preparing these things. If from circuit to circuit they're going to be randomly all over the place, how do I learn anything from that, right? But if I can get a way to make these circuits very reproducible, the impact is phenomenal. Right. Why? Because I can replace a normal neuron with a neuron from, say, someone with, let's say, with dementia or some various mental disorders, right? And then we can actually start studying, where is the problem in the way these neurons are communicating with each other? Could be very interesting, actually. And you can also take such neuronal circuits, can add some medicines to it, and then see whether the quality of the circuit improves, that sort of stuff from drug development, So I think there's really a tremendous possibility here. So, this is the Yale Neurosyntech collaboration. There are a lot of challenges here. For example, reproducibility of the network, standardization of chip production workflow, ability to regenerate chips with fresh neurons, preserve learning outcomes of training processes. Challenges are reproducible only contacts in neurons, which I think would be a very important issue. Axon connection to adjacent neurons. How can we really reproduce it again and again? And how do you control the dendritic connection, which is really hard. It's like a very random process, basically.
Why is it hard for the dendritic connection?
Say it again.
Why is it so hard for the connections with the dendritic structure?
No. It's not hard. The dendritic connection is totally stochastic. In other words, the neurons do what they want to do. You can't really control
Right,
it.
right, right. You can-
Axon, I can at least force it to go in one direction because one is one
Right,
axon,
right,
right?
I understand.
The dendrites of each of all of them, yeah.
Earlier you mentioned you want to input a stimulus and see what the neural circuit
Right.
does, right? So you
Right.
could, in a sense, stimulate through your CMOS chip connections the specific neurons you want to promote connections between. So you have the axon dendritic connections and you promote that growth
Yeah.
and demote, I guess, the surroundings.
Well, I mean, you're now getting to the concept of what I call, neurotransmitters and, neuroinhibitors and those
Yeah.
kind of ideas, right? I mean, that's what happened to us, right? When I drink alcohol, basically, I have the neuroinhibitors, basically, which goes and effectively adds a weight function to all these dendrites. Its weight is equal to zero, all of these kind of things. So you become really calm and, everything, you literally kill all the excitations in some sense, right? And the question is, can we do those sort of stuff, electrically stimulate these sort of stuff? That's really the whole idea, that's the reason for doing these sort of thing eventually. But right now, my thing is, I would like to learn how these neurons are really communicating and what's really going on in the system. I mean, there are glial cells, the many things in the neuronal circuitry that are in the biological system. There are things called glial cells that float around. They play a very important role in the growth of the neurons. We don't have any of those stuff here, right? I mean, we really stripped everything clean here in some sense. So this is a very different kind of a system. So how do these things behave? How close could they be even to a realistic system? We don't know the answer actually. I mean, what I feel is like these are really far-reaching experiments that you'll be doing. They will be very challenging, but in my mind, they think these are the kind of stuff we need to do in the future to really understand the biological systems. Anyhow, so with that, I'd like to say thanks to you guys for listening to me.
Thank you very much.